So let's say I wanted to find the distance between 2 points on a linear graph, A and B, and I knew the coordinates of A and I knew the coordinates of B. So how do I find the distance? Well, you can see that this distance between these two coordinates lying on the x-axis, this distance here, is the same as the distance over here. I'm just going to lift up this length to this level. And this distance is the difference between these two values. I'm going to call this delta x for difference of x. And this distance here between the two, that lies on the y-axis, between the two y values, is the same distance over here. I'm going to call this delta y, okay? So you realize that because these lengths also lie on the x and y axes, they're perpendicular to each other because the axes are perpendicular to each other, which means this is a right angle. That means I can find this length by using the Pythagorean theorem, okay? So this squared plus this squared equals this length squared, okay? So that means the length of that length that we're trying to find, length AB, which is the hypotenuse, you can think of it, is just going to be following the Pythagorean theorem. So it's going to be the square root of delta x squared plus delta y squared, okay? Very simple, very simple. But what if we want to find the length, not of a line, but between the 2 points of a curve instead? That's going to seem a bit tricky because it's not a straight line where you can actually use the Pythagorean theorem. Or so we think. The thing is, we can kind of approximate the length between 2 points. Let's just pick two random points. I'll pick this point. I'll call this one A. I'll pick this point. I'll call this one B. I can approximate the length by maybe drawing a line and treating it as if it's a straight line. It's not really close. There's still a lot of excess length on the actual curve, but it's kind of close, but it's not really correct. So why don't we just try again? How about, to make it even closer, let's make it 2 line segments. Wait, that's a little curvy. That's not a line segment. That's a curve. So yeah, maybe I can find the length between these 3 points, this line segment, but there's still some error. There's still some excess lines, and maybe I could do it again. I could actually draw even more line segments. Maybe I could be more accurate. One line segment here, another line segment here, another line segment here, another one here, another one here. You realize it's getting more and more accurate, but there's still some error. It's not exactly the same as this curve. So the thing about curves and trying to find lengths and areas and derivatives and all these things is that we can always keep getting closer and closer the more we do it, okay? The more line segments we add, the more closer and closer we get to the value, right? So as the number of line segments approach infinity, the length of all the line segments combined approaches the actual value, okay? And if we can see what this approaches, we can actually get the actual value. Without actually being able to calculate it, we can see what it approaches. That's how limits work. So all we have to do is just find all the lengths of these tiny little line segments that are basically infinite in number, okay? And add them all up between the 2 points A and B, and then we can get the actual proper length. Now that seems like a lot of work. You're taking a bunch of infinitely small line segments, an infinite number of them, adding them all up. That's too much work. Well, maybe we could use some operators that we know from integration, right? Integration has this operator, this weird looking S sign, which is basically a summation. It sums up a bunch of terms. Let's say if it's this of y, it's summing up a bunch of y terms, and I just have to give 2 boundaries. A is supposed to come first. Whoops. A and B, give 2 boundaries. It basically sums up all the y values from the A to the B point, and basically conveniently adds up infinitely many different terms. And this dx operator, this dx, multiplies by this value of dx. It multiplies every single term that is in this infinite sum with this value of dx, okay? And we can, and you know how we use this for area, right? By adding up a bunch of tiny rectangles. But instead, we're adding up a bunch of tiny line segments instead. It's different now, but it's a similar concept. We're still using the similar operators of integration. See, integration is all about adding up infinitely many things, but doing it in a finite amount of time with some, special techniques. So how can we find the length of all the tiny little line segments? Okay, so why don't we just analyze one line segment first? I'm going to draw one line segment on this curve. It's not on the curve. It's kind of floating off the curve. Okay, so like this. Okay, the line segment is a straight line, while the curve is a curved line. Okay, so it may look like it kind of coincides with the curve, but if you zoom in even further, you will notice that it deviates. The curve deviates from the line because the curve is a curve and the line is just a straight line. So if I were to kind of zoom in and see how this straight line looks, amplified, I'm just going to draw this like zoomed in view. You can see that this is the line, and the curve will probably be here. It'll kind of deviate a bit from the line, but we don't need to care about the curve now. We only need to care about the line. We need to care about the approximation, how to find this approximated value. Okay, so similar to what we did with linear graphs, we can treat this as if it's a linear graph, right? We can treat this as the length of a linear graph. We have to find the change in y values to find this length over here, and a change in x values to find this length, and we can just apply the Pythagorean theorem, remember? But because it's so small and it approaches 0, this base of this triangle is not delta x. It's delta x when it gets so small. It has to be dx, right? And this one is dy, okay? Because it's the change in y, but getting so small. So to find this hypotenuse length, we just have to do similar to what we did before, dy squared plus dx squared. See? Pythagorean theorem, very simple. So all we have to do is add up all these guys across the different y values, against various different points, add up all these tiny things, and we get the actual proper length. So how do we do that? Well, we can use the integration operator again. So we just do this, show the value that we got before for the hypotenuse, and add them all up. Add up all these guys. Boom, done. Oh, and we just have to give the boundaries, which is probably going to be from A to B. Done. Wait. Can he do this? The thing is, we can only do integration when there's a dx at the side multiplying. We can't really do that here. We can't. The thing about the dx at the side, it helps us find the antiderivative of what's inside here, while there's supposed to be some dx over here. But there is no dx over here. So how do we get a dx over here without, changing this proper value, changing what's inside here? Well, what we can do, we can put a dx over here and divide a dx out over here so that they cancel each other out, and we can still, we can still kind of get the same value. We're not changing what's this value going to be. So we need to see how this actually gets in here. We can put this inside the square root to make this even better. Okay, so this is going to be, I'm just going to rearrange some things. So this is going to be 1 over dx at the side here, square root of dy squared plus dx squared. Now, if I square this whole thing and I square root the whole thing, it makes no difference, right? That means I can join these two together, by the nature of how square roots work. I can join these together under one square root radical sign. So basically, I can combine them by having the square root of 1 over dx squared multiplied by dy squared plus dx squared. Okay, so I can distribute this now. When I distribute this, I end up getting something that looks a bit better. So there was a dy squared, but it's dividing by dx squared, so it ends up becoming dy over dx whole thing squared plus, then there's a dx squared here, divided by dx squared, just becomes 1. Whole thing dx. Now this is something you can actually deal with, right? It's very difficult to deal with just dy and dx, but we can deal with dy over dx. We know how to do that through differentiation, right? Very simple. And we have a dx at the side, so we can use our common integration techniques. So yeah, that's basically how to find the length, the arc length, between 2 points on a curve. Which is quite crazy, right? Like, this is kind of the Pythagorean theorem. This is the Pythagoras theorem that we use for, linear graphs. But we're doing it on like a tiny scale and adding up all these individual parts and in this infinite sum of integration to get us the actual proper length. So yeah, it's quite wild how we can, take very common things in regular geometry and make it so small and tiny, but make it approach infinity to make it work for curves, So it's quite amazing how we can use integration to take these normal ideas and make it, you know, more applicable and really to curves. Like, yeah, okay, I don't know how to end the video. I don't know how to end the video. Never mind. Yep, that's it. That's the end.